Hey, hi everyone. Very good evening. Hi, Govind. Good evening. Hi, Srisha. So, is my voice is loud and clear to you all? Online ones confirm. Hi, Harsh. All right. Clear? Perfect. All right. So, let us get started now. So, before we get into today's topic, can everyone do a quick recap on the things we discussed till now? What are the topics we have covered in yesterday's session? What are the topics we have covered in yesterday's session? Yes, parameter calculation. We looked at parameter calculation and yes, Srisha, transfer learning, dropout function, VGG16, VGG19. Perfect. So have you all tried working with the other architectures like InceptionNet and everything? Hush, different image processing models, right? Yes. So if you haven't tried, I think we have given this basic template of different CNN architecture. You just need to change this number of inputs based on your architecture, and you could see a big difference with respect to the timeline and everything. So once try changing that, so it should work. All right. Maybe during this weekend, you can just give a try on it. Perfect. So let's get into today's topic. So today we are going to get into one topic called as autoencoders. So autoencoders is nothing but as per the agenda, we thought of getting into this particular topic, that is detection algorithms. So let me share you this particular thing. So after completing this particular part, that is CNN, there's three things. Sort of getting into this detection, but what we will do is again, one more image processing thing is available with respect to the same CNN architecture. So let's take this image pre-processing, that is autoencoders theory and also script-wise today. And then we will get into this detection algorithm tomorrow. Okay, so today's session, it's going to be 1 to 1.5 hours of session, and then we will be winding it up. So see this autoencoders. So this is what we are going to do it. And let me explain what exactly this autoencoders will do. Before that, let me do a quick recap on the topics what we have discussed till now. So we just deep learning. So basically, we understood what is the difference between machine learning and deep learning, and we worked on this MNAST script after understanding this different optimizers, different activation functions, different loss functions, how exactly that would work, and then we got into this particular topic. And then we understood CNN. CNN is all about extracting this important features from this particular image. That's what the CNN is all about. And then we worked on CNN architecture, and then we learned about transfer learning concept. And with respect to transfer learning, what is this transfer learning? Already a model has been built, and we are using the intelligence of that model, and we are transferring that intelligence for our use cases. So we are having our own folders, and we are having our own files, and we are using that intelligence of the pre-built model, and it is just going to make a classification for us. That's what we have worked on yesterday. And today we are going to continue this autoencoders part. So what exactly this autoencoders? Let me give you some applications. So autoencoders is nothing but we are already using it. That is, whenever you're using this any applications like photo editing applications, now you would be giving some blurred image. Now let's say your image need to come out of that blurriness, and it need to be pretty clear. How can we do that? With the concept of autoencoders, we can do that. And you're having some black and white images. Now you wanted to convert to a colored image. How can we do that again with respect to the same theory, autoencoders? There are a lot of other applications which we can do with respect to autoencoders. Now, how exactly the architecture of autoencoders? Let's take a read on it. But before that, see this. This is again one small theory. All right. So there's a few applications here I just listed. That is noise reduction and color image colorization. There are a lot of other applications of this autoencoders. So why we are using this particular architecture? One is for noise reduction and the other one is for image colorization. Now what I'll do, let's understand the architecture the same way how we have learned the CNN architecture and VG16. Or whenever I say autoencoder, so it is also having its own architecture. Now how exactly this architecture of autoencoders will look like? Let's get into this Google. And let's try to understand this. Let me share the screen. Autoencoders architecture. See this. What exactly autoencoders? Here, let's take a read on it. Autoencoder is a type of neural network that can be used to learn a compressed representation of raw data. An autoencoder is composed of an encoder and a decoder submodels. The encoder compresses the input and the decoder attempts to recreate the input from the compressed version provided by the encoder. All right, let us take one more time. Read. Autoencoder is a type of neural network model that can be used to learn compressed representation of raw data. Basically, during the training part, what we do, we are supplying one blurred image, and that blurred image will be compressed and it will be represented in a small dimension. An autoencoder is composed of an encoder and a decoder block. Basically, that's what we would be having an encoder to compress the image and the decoder to expand the image to give us in a clear format that is taking out all this particular blurriness and the noisiness and everything. So this is the architecture. Just take a look on it. Let me click on those images. Yes. Let's take a look at it. So this is going to be your input image. Okay. This is going to be your input image. You're going to take your input image. You're going to compress it by using some convo layers and downsampling layers. And your latent space representation is nothing but otherwise we call it as bottleneck. Now, what is this latent space representation? Your full image, let's say it is 128 by 128 or 28 by 28 image size, you're reducing it and you're reducing it to one dimension, let's say 7 by 7 image or 3 by 3 image, something you're taking it. And from this 3 by 3, again, we are using a decoder block where we are expanding this particular network to reconstruct our image. Now the input image is going to have some blurriness and the reconstructed image is not going to have some blurriness. So this is the architecture of this autoencoders. I would be having one encoder block and then space representation I will be handling it. And then a decoder block, I will take it and I will just expand this network and I will be reconstructing my image. So this is what this autoencoders architecture is all about. Now with this particular thing, let's just go back and take a read on this material. See this, a quick reminder to machine learning. So we learned how exactly we can represent the whole data from an input image in a latent space representation. I'm not getting this particular point. Let's understand this. See this, all the data is represented by the equation y is equal to mx plus c. That is machine learning. We learned about one machine learning algorithm. So what is that algorithm? That is linear regression. So linear regression is nothing but what? This is what x and y we have. So this is my points, right? So where exactly if I'm drawing this particular point, sorry, this line is a representation of all the points just mentioned, right? Maybe the points, maybe they're scattered around like this, but I'll take this point and I'll just make sure most of the points are falling onto this particular straight line, which means that what finally, hey, this line is the representation of all the points, whichever it's falling onto this particular graph. So in that particular pattern, what is the equation of this? Y is equal to mx plus c. So all the data is represented by the equation y is equal to mx plus c. Statistically speaking, that linear line is a representation of all the data points that are scattered around. Similarly, neural networks represent the relationship between your input data and your output data. How? Neural network represents this X and Y as a function. It is nothing but it is not something linear. It is a function of a function of a function, and it depends how deep the network are. Now, what is a function of a function of a function? Now, here you're having input layer, right? Input layer. Now, hidden layer 1, hidden layer 2, and hidden layer 3, convo layer, and then output layer. Here I'm having neurons. Here I'm having neurons. So what is this H1 if I'm just saying activation function multiplied by input? And here H2 activation function multiplied by input. Now, if I wanted to make an equation of this, what I would do? Again, one activation function multiplied with this. So which is again an activation function. Again, an activation function, it's summation of all activation functions, I'll be getting it. Which is nothing but what? This is function of a function of a function of a function. In this way, it will, one neuron is nothing but what? It is going to be a, this neuron is going to be represented as a function of a function of a function. So that's the same point which I mentioned. It's not something going to be linear. It depends how deep the network are. As the computation ability improves, we can expect the network architecture to become more complex and more complex. So why most of the live applications that we are trying to solve are very complex. That's the reason why this even BG16 and BG19, that networks are much deeper compared to the architecture what we built. There are several neural network architectures to understand the complexity of the data. Then what is this autoencoders? See this. What is this particular autoencoders? If you read, autoencoders are neural networks where you have a specific architecture like AlexNet, LeanNet. So we have already seen the architectures of AlexNet and LeanNet, how exactly it looks like. But it is not going to be that complex. However, the architecture is designed in such a way that output is the input. Marked on this particular term. The architecture is designed in such a way that output is going to be the input. This is one key term. Once we get into the scripting part, you will understand this particular thing. In other words, autoencoders are the neural networks which is designed to reconstruct our original image. This point is a very good example. Very good the point here we can say. Autoencoders are the neural networks which is designed to reconstruct our original image. Right? This is going to get reconstructed by removing the blurriness, by removing some noises. So if the image, if it is completely damaged, we can just reconstruct it by just fixing some patches on top of the image, making sure, hey, this image is an original image. We used to do that in Photoshop and something. So now, so left-hand side, the input is going to be an image, or it can be a damaged video, or it can be a damaged video or damaged image. It can be encoded much smaller dimension, and that's what we are representing it in the slide in space, and then can be decoded then to reconstruct the original input image. It can be audio or video. So able to get my point, everyone? Why this autoencoders? The theory, getting an idea? Srisha, Jyoti, perfect. So once we are going to get into the scripting part, and then we will be winding up our session. See this, how that's possible. As you're in this process, you're training the network and your weights and biases are adjusted accordingly. All right. So here we are providing the same input X and we are getting the same output Y. Approximately. So same output Y approximately. Because the input is going to be a blurred image, the output is going to be the same image, but removing the blurriness. That's what we are saying. Output is nothing but the input, but with some reconstruction. But you can notice some sort of difference in your output. Why? Because the input is having sort of noisiness and your output with the same image, removing that particular noisiness. So it can be a bit darker, lighter compared to your input image. So we can say that the input will be approximately equal to the input image. Sorry, the output will be approximately equal to the input image itself. But it can never happen practically because your output will have some sort of loss when going through this kind of training. So here, if I'm saying loss, if I wanted to reproduce the image with the same image, then like blurriness is the input. And if it is produced the same image, then what's the point? So from the, you need to go through some laws so that the noisiness is going to get removed. So the whole idea of autoencoders is nothing but you have your input data and the input is reconstructed back. What is it input data? You have your input data with some blurriness or with some damages. So I wanted to reconstruct that. So that's the major idea. So now note we are you having encoder block and decoder block. In encoder block, we are going to use something called as max pooling layer to reduce the dimension. And in decoder block, we use something called as upsampling for reconstructing back. So this theory is fine for us to get into this autoencoders. Now what we will do, let's open up a new Jupyter notebook and let's all start to scripting. Okay. So, and then after understanding the scripting, I know few of you would be having some questions, how exactly this can be done, what is this reconstruction, everything. But let's get into scripting part. Post that if you have any queries with respect to the theory and also script, you can just ask me. I would be helping you to understand that better way. All right. So let's all open up our Jupyter notebook. Let me share my screen. So let me share it. So we are, where's it here? Okay. So deep learning, let me create new Python 3. This is nothing but autoencoders. Let me create autoencoders. So the first point is nothing but, so for doing this autoencoders, what is the idea behind working with respect to this? Nothing but we are having one image in our hand, that is MNAST data set. We will take that, we are having Xtrain, which is having some images, right? So we are going to feed some noisiness to that image, and then we are going to remove that particular noisiness. All right. So that something we are for understanding this particular concept. So let me import. First step is nothing but import necessary. Let me import necessary libraries. So let me import it. So what are the libraries to be imported? So we use this Keras, MNAST data set and everything. So what I'll do, so from Keras, first let me just see from TensorFlow, import Keras. And what are the other things? From, let me do this first so that we'll get all this shortcuts. All right. So from Keras, now from Keras dot, let me give tab button, this datasets, let me import tab button, MNAST dataset, and then from Keras dot models. Even from Keras, we can import the sequential model. And then from Keras, we need this layers, import. We need this, what is it, convert 2D layer we wanted. So that's what we will be going for this for feature extraction and everything. So we need convert 2D, and then we use something called as upsampling. First we have to downsample. So DO, what is that? Sorry. So upsampling we need. Max sampling is for downsampling, right? Max pooling 2D. And then we have upsampling 2D. And then what else? Then flatten layer. Do we flatten it? We don't in this particular part. So here we can just directly get into this dense layer. So that should be fine. So now, all right. So these are the necessary libraries. I've imported it. Now the second step is import data. All right. So how to import this data? Already this MNAST has been imported. So MNAST dot, if I give load data. So let me give this, and this will be stored into. So it returns a tuple of two things, right? So how do we do that? Xtrain, comma. How it is done? So let me check in keras.io. Get started. Let me this website, so Keras API reference. So here, built-in datasets. So whenever you're having any questions or doubts, you can just come on. Extend, understand? So extend, comma, white, comma, xtest, comma, y test. All right, you can just check it out. Extend, so now it is data understanding. Third point, data understanding. So how to understand just the same process. Extend, comma, shape, comma, y train, shape. All right, we have. Now again, xtest dot shape, comma, y test dot shape. All right. Now, this is what the data what we have. But in case if you're referring any internet or something, you can see something called as extend comma underscore. In case if you're finding out, so you'll be having this kind of underscore. Now, what is this underscore? This nothing but see this. I want only images. So here we are not going to give for any supervised learning. So autoencoder comes in your unsupervised way of learning where we are not going to provide the output. So basically the point is nothing but, so here I only want the images. I just want only the images, not the labels. Labels is nothing but 1, 2, 3, 4, 5, just a kind of integer format. I don't want this. So if that's the case, maybe only for practicing purpose, what so not only with respect to MNIST, with respect a lot of other data sets, if you're finding this underscore, so that means that, hey, I don't want this particular white train, I don't want this information. Now let me again reload. Now if you're instead of this white train, just if you give underscore also, it will give you the same answer. See this? Underscore, it will get stored here, but it means that, hey, I don't want this information. So why do I need to carry this? So this is what they would be giving. So is this point understandable? Is this point understandable? Confirm everything. I don't want this underscore, which means that I ignore this. Please ignore. That's it. In case if you want, basically, what is the purpose of creating a variable name? And I used to say create some meaningful variable names. So here I'm not even creating variable, I'm just an underscore, which means that what I don't want this output labels for this kind of study. That's what the point. All right. Fine. So now the next step is nothing but data understanding is done. Let's go for data pre-processing. So what are the data pre-processing steps we do? Data pre-processing. We try to reduce the variance, right? We try to reduce the variance, and yeah. So strain, that is mic strain data divided by 255. You can just check out now. Strain dot standard deviation comma x test dot standard deviation. So looking into it, more variance. So to reduce the variance, x train divided by 255. X train now, and then x test divided by 255. X test. All pre-processing is done. Now you can check it out. I'm storing into the same variable. Dot standard deviation. All right. Now the variance got reduced. All right. Now what I wanted to do is nothing but so I just wanted to whenever I just wanted to give to this particular network, I wanted to say whether it is colored image or black and white images. All right, which means that 60,000 images of size 28 by 22. But here, before giving into this particular model, I need to have this particular model in such a way that, comma, this channel I have to give it, whether it is one means it is a black and white channel, comma, 3 means it is a RGB channel. So this input need to be changed. The input size need to be changed. So not change, it need to be altered in such a way that just I have to add one within this particular part. So to play with this kind of numbers, I need one library called as NumPy library. So with respect to this NumPy library, I can reshape my complete image. So how do I do that? See this. So firstly, I'm importing this NumPy here. Import NumPy as NP. All right. Now let me come back. NP dot. Let me give a tab button. There is something called as reshape. So within this reshape, I'm just giving it. What is this? A is nothing but your array like. Let me copy. A new shape. What is the new shape that you want to give? Array to be reshaped. A is nothing but array to be reshaped. Now what is that? Let me just give it. A is equal to my x string. A is nothing but my x string. And new shape. What is the new shape that I wanted? In which format do I have to give it? See this, it should be tuple of integers, right? So I'll just give tuple of integers. New shape is equal to 60,000 images, comma, 28 by 28 is the size, comma, 1. So with that, what I can do, I'm just reshaping my particular image. Well, now it is done. The result, let me just store it into xtrain, xtrain underscore reshape. Let me just store it like this. All right, it's reshape. Now we can just check out xtrain reshaped dot shape. If you give it, see this, 60,000 images of size 28 by 28 of one channel, which means that it is a black and white image. In the similar way, I have to do it for my test images also. So what I'll do, let me take this out, maybe, or first line, np dot, or we'll say, let me copy this, copy, let me paste it, next test, underscore reshaped. So now here I have to take x test. Now you can see xtrain reshaped, come on, x test reshaped dot shape. If you check it out, why it is throwing an error? Okay, already it's been, all right. So first cell, because already it is in 28 comma 28 comma 1. When I'm executing it again, it is just throwing me an error. So that is a problem. I'll do one thing. Let me again put this. Just check it, 28 by 28. So this one standard deviation. Let me do it. Now if I'm executing, oops, which line cannot reshape of size. What is the problem? Exist. Okay, see, it's 10,000. Sorry. Here the images is 10,000 image, 10,000 28 by 28 by 1. Yes. Now if you see 60,000 images of size 28 by 28 by 1, 10,000 images of size 28 by 28 by 1. All right. So now I've just done this particular part. Now this necessary pre-processing is done. Now I'm just going to add some noises to train and test this images. All right, because with respect to noises, I'm going to give it to this encoder blocks. So let me just give it. Next one is again, let me give add noises to the input data to give to encoder block. All right, to give to encoder block. Now, how to add this particular noises? Firstly, let's try to take a look at how exactly this image will look like. Now I want to visually see my image. So how do I see it? I want this matplotlib library. So let me go back. Let me import this matplotlib library. So from matplotlib, let me import pyplot as plt. All right, plt. Now let me come back here. Plt dot. I'm having something called as image show. IM show. It's nothing but what image show. So firstly, it will take image, right? Image and color map. Let me do it. Control C. Let me paste it. This is nothing but let's my extract of the 0th image. Let's say of 50th image. And color map, I think we already know how to do it. So that's nothing but I want this gray color. And plt dot show just to show only the images. Okay. So now particular noisiness. Noisiness in the sense only image I am able to see. There is no noises in this particular image here. Now I'm just going to give some noises to this particular image. Now what I'll do, let me just give a title to this. Like this is before noise. Before noise. Now let's add noise. Add before noise. Now let's add noise. Now how I'm just going to add some noises again with respect to this NumPy library itself. Now what I'll do, see. So this is my extrain reshaped images. All right. So with respect to this this reshaped images plus I'm going to add from this some random numbers already to this particular input image, all the input images, I'm just going to add np dot, there is something called as random dot rand n. A lot of ways how you can just add it. Sorry, yeah, let me add it normal distribution. Let it from distribution. So normal distribution, nothing but what? So within one standard deviation, I'm having 68% of the values, two standard deviation 95%, three standard deviation 99.95%. So from this normal distribution, I will take some random values, and again within this, if you see, we've already seen this particular thing. LOC scale and also size. LOC is mean, scaling, but standard deviation. See this? It is going to draw random samples from a normal or distribution. You know how exact that random distribution, normal distribution, everything. So which means that what mean is 0 with a standard deviation of 1. I'm going to pick up some random numbers. And what is the size of this? We have to give it over here. What is the size of our particular image? It's nothing but 60,000 images of size. 60,000 images of size 28 by 28 by 1, right? So this part, let me just try to give it to my extrain something like, let me create noisy. Okay. In the similar way, let me try to do it for my X test reshape. To this also let me add plus np dot random from a normal distribution. Let me take this particular part. Let me copy. Paste it here. Sizes for the test data 10,000 images of size 28 by 28 by 1. So let me store this into X test noisy. Shift enter. All right, now it is done. Now what we will do is nothing but again, let's see one image, how exactly look like the same image that we copy. So same image, Control C. Now here it is, extrain noise it is. Noisy, now see this. Oops, there is a lot of noises. Image itself actually noise I've just given it here. Right? So there are a lot of noises which we get. Now we have to reduce this particular noisiness. So it is going to say 0.5 maybe. But see this, we are able to reduce it, but more blurriness it is able to come. So now what I want to do, number itself, it is not visible. So this is more noisy. This is very much difficult to take it because everywhere I'm able to see black and white images, it's more mixed up. So what I'll do, let me not touch this particular part or let it be 0.5, not a problem. So, but what I'll do now, I'm going to introduce something called a clip concept. All right. Again, with respect to step number 1, maybe we'll just make it as step number 1. Yes. So here with respect to normal distribution, we are doing it. And the next part, two, step two, clip your image. Now let's step one. Step one, add some noise. Step two, but clip your image. Now, what does that clip your image is mean by? See this. Again, np dot. There is something called as clip. You have it here. Clip. Clip. The values range. In an interval, values outside the interval are clipped to the intervals. For example, if an interval of 0 to 1, a specified value smaller than 0 becomes 0, and all values larger than 1 becomes 1. So now what will happen, because here this is the value that we have to give it, because it's a range between -3 to +3, and that's how this particular values has been taken from. So now what I want to do is nothing but any values less than 0, I wanted to make it as 0, and any values greater than 1, I wanted to make it as 1. But if it is like 0.53, 0.34, that value it will be coming. I'm not going to disturb that particular point. So that way I want to do it. So let me try this particular part. So let me copy. Let me see whether this would work. Now what is this A? A is something but array containing elements to clip. That is your extreme noise. Extreme noise. And I want a minimum value of, let's say, let me take it from 0. And let me maximum value, let me give it maybe 3, something. Right, I'm just clipping it. Let me store it into something like extrain clipped. Extrain clipped. In the similar way, xtest, sorry, np.clip. Let me clip my A is equal to the same function here. Xtest minimum value is equal to 0, and A maximum is equal to 3. The same thing let me do. Just need to get stored into xtest clipped. Now this is what I wanted. All right. Now the same. Let me see this. Now it is extreme clipped. Now see this. All right. Now the noisiness is bit reduced, but again the number is not much visible because earlier it is a lot of whiteness I was able to see. That we have just reduced it. So that's point. Maybe let me just increase this one to 1.0. Now let me again do this. Maybe let me just give it to 2. Oops, lot of blurriness. Maybe let me just give it 4. Still, it is not so clear. Maybe let us look at some other images. Maybe how exactly other images are looking like with respect to it. There's more noisy if you allowed it. And let me clip this particular. Anyway, let's take it and see how a lot of noisiness here. This page is 3. Image itself, it's not clear. So max value of 3. Let me give it. It's not clear. Let me take it from -1. Oh, niceness. This is 5. Let me get. Oops. All right, let's anyway go and see how exactly this is able to make a prediction and see whether it is making sense or not. clip function is actually going to remove, eliminate the less. See this, it's a normal distribution, right? It can hold the values from negative and positive values. Now I wanted to clip it. All the negative values, I want to make it like 0. Like your activation function. What exactly your real is going to do? All your negative weights is just going to make it like 0. And the positive values, it's just going to give it the same value. In a similar way here, I just wanted to give some limits. We can say activation function, minus and plus 1. Got my point? Yes. So here at least I wanted to reduce some noise, but more noises here I just given. Let me do one thing. Maybe let's just multiply some number with it. 0.2 multiplied by some number. With this particular thing, let me multiply some linear number to this. Oops. Okay, now it is clear. See this? Now I just added some number to this normal distribution because everywhere it's a normal distribution. So I'm just making it a little bit uniform so that it is, if it is getting multiplied by 0.2, the numbers will be a little bit uniform. So now this is a third image, and now the third image after making this to this. All right. Now see this. There is a little bit of noise here. I'm just giving it a 3. Yep. So there is a little bit of noisiness over here. All right. So what I wanted, this blurriness or this noisiness, I wanted to remove so that it need to be bit clean. And this, I wanted to have a very neat image. All right. So that is what my goal with respect to this particular data. Now, data pre-processing is done. So we just imported the necessary libraries, we imported our data set, and then we understood our data. We went for data preparation. The step is model building. All right, let's go and build this particular architecture. This is step number fifth step. Model building. So what is that particular model building? Let's just start with sequential model. Model dot add. Let me just give it here. So within this, firstly, I just wanted to add this convert 2D. All right. So what is the input image if I'm using it? It's a copy. So what is input image size? It is 28 by 28 by 1. Right. So that is my input image size. What is the filters and everything? Let me just use it here. Come on. Filters. Let me copy. Filters equal to, let's say I just wanted to use maybe 32 filters at the first layer. 32. And kernel size. Let me go with the kernel size 3 by 3 or 5 by 5, anything let's select. Let me go, since it's 28 by 28, let me go with a small kernel size 3 by 3. Come on. And strides movement. Let it be 1. And now padding. I just wanted to give padding. Let me give padding is equal to C. I don't want to reduce this. Only at the maximum layer I wanted to reduce. And then activation function. I wanted to tweak it and I wanted to give it to real activation function. All right. And this model.add. All right. So convo is done. And the next layer is nothing, but I have to downsample it. For downsampling, I would be using max pooling layer 2D. And within this max pooling for 2D spatial dimension, downsamples it. So the first architecture is pool size. I wanted to go with 2 by 2. Pool size equal to, let me just go. Pick a matrix size of 2 by 2. And then strides is equal to, strides also is equal to 2 by 2. That's what I wanted. So now let's say model.summary. So what is it here? activation. Okay, here one round bracket. What's the variant? Fine. So now 28 by 28, when it is going through max pooling, 14 by 14 of the same size. Now, one more convo layer, let me use it. Let me again downsample it. Let me again downsample it here, but this time maybe let me use 8 such input image. I don't want it. Filter size, let me reduce it to 8. Padding fine and size equal to right. So 7 by 7 by 8. So now from this particular 7 by 7 by 8, so let me again use one more convo filters. Again, let me downsample it. Copy. This is my encoder architecture basically. I'll do the same thing. Now, if you see, we are representing our image in this particular format. Maybe we'll just do this from the 7 by 7. All right, from the 7 by 7, I wanted to have see this. If I'm going with a size of this one, 7 by 7, 3, 4, 5, 6, 7, right? Oh, so I'll just go with the size of 2 by 2. So if I'm just going with 2, 3, and one more thing is also available, correct? This is 7. So this one is missing. So when I'm just going with the max pooling layer, even to if I'm just not giving padding is equal to same, this column will be completely missed. So when I'm going with the max pooling layer also, since I wanted to have the zeros here so that I can just pick up the maximum pixel at the corner. So what they've given within this max pooling layer, they have given this particular padding option. Let me give a comment. So read this. Sorry. Max pooling layer within this. There is something called as padding option they have given it. So this padding within max pooling layer. With this max pooling layer, I'm having padding. So in case, why I'm just purposefully saying, because it's now, in the earlier case, it is 14 by 14. I'm going with the strides of 2, so not a problem. But now the convo size is 7 by 7. If I'm going with strides of 2, the last column, it will be excluded. So, but I don't want that to happen. So I'm saying to same at this particular level. Got my point, everyone? Why I'm just giving padding? Now, if you look onto it, let me erase this. Now let me look onto this. So here, what is the thing? Padding. Okay, see this I want to take it within this one. Cover comma. Yes. Got it, everyone? Why I'm just giving padding? Now if you see 4 by 4 by 8, is this point clear? Let's confirm. Jyoti, yes. Others. Srisha, Jagdish. Perfect. So now this block, what I've just constructed, we call it as an encoder architecture. Now in the similar way, I will just construct my decoder architecture. Let me just give it. This is my encoder architecture. Now my encoder architecture is 4 by 4 of six such features I have. So this is my latent space representation. So this 28 by 28 size image, now I'm representing it in 4 by 4 of 8 such filters. Now this image I want to decode it. So for this, let me just write my decoding architecture here. See this. Let me write it down. Decoding architecture need to continue from this particular part. How exactly the last layer sizes, and from here it need to get continued. Now this is my decoder. Still now I'm not supplied my data. You will supply it in. So this is model construction, and then compile your network, and then in model training I'm just going to give my architecture. All right. This is my decoder architecture. That is again to this particular model.add. Let me add this. What is that? First I have to go with the, because now it is max pooling. So let me just give this particular convert 2D. Convert 2D. Now we have to take this particular for the same thing what I've already given here. That is how many filters I've used it. 8 such filters, kernel size of 3, strides equal to the same thing. Let me copy it from here. That is the last layer. Copy. Let me paste it. So this is the last layer. Now after this, let me add downsampling. So from this particular part, sorry, I have to increase this particular sample size. So what I'm doing, I wanted to go for this upsampling part. So what I do, upsampling layer, I've already done it. So sorry, imported it. So upsampling is nothing but what here arguments you have code arguments. So size, what should be the size? Tuple of 2 integer. So from this, size is equal to, and what size we can give it from here. Let me just increase this particular size by 2 by 2. All right. I wanted to increase this particular size by 2 by 2. Now let me say model. After increasing this, again model.add. Again, I'll be using this particular convert 2D because that's the second layer. If you look onto this previous layer, before this convert, again used 8 such filters. Padding is equal to the same thing. Because here, if you see, pools is equal to 2 by 2. That's why I just given upsample 2 by 2. And let me add the same thing. All right. And after this, and again, I will be using before this particular part, what you have used. Again, pool size of 2 by 2. So let me use this, the same thing. Copy 2 by 2. And then what I would be using, again, I'll be using this particular, how many such filters? 32 such filters is used it, right? So let me copy this. Sorry, only this particular input layer. Input shape I not require. From filters till activation function, let me copy. Let me add one more layer. Add convo. Because here from here slowly we have to go to this particular level where exactly the output decoder output should be 28 by 28 by 32. So that's what we are aiming for. So 30 such filters. Now the upsampling should be again to upsampling. Let me give the same size of 2 by 2. All right. Now finally, what should be the size of this particular image? What 28 by original image size is nothing but what 28 by 28 by 1. So that is my original image size. So what is the problem here? It is turning in red color. All right. So what I'll do again, let me copy. Let me paste it. Now the input image size is filters is nothing but 1. And kernels, do I want this particular kernels here? Let this kernel be here. And padding activation function, that's it. So this is what I want. Now if I'm just looking on to why these brackets, okay, I think everything is perfect. One more bracket. All right, now if I'm just looking into model or summary, I want the final report, it should be 28 by 28 by 1. Filters, where is that? Okay, here convert 2D you have to add it, right? It's a convert 2D. Convert 2D. And if that's the case, one more bracket. Bracket. Fine. All right. So now see this. Okay, it is executing 2 times. Now what I'll do, let me 10th convo layer it is. Okay, complete layer, I'm just getting it up. 4 by 4, 8 by 8, 16 by 16. It is going for third layer also. So this one I don't want it. So it should be 28 by 28 by 1. So that's what the size should be. So here, let me see. So here, Let me not use this particular padding. Let me not use padding. Again, let me come up with this architecture. So 28 by 28 is 4 by 4. And then, okay, here it is upsampling and convo here. It is happening 28 by 28. So see, based on this architecture, we have to tweak this padding. So upsampling is done by 28 by 28. But here, if I'm just giving padding is equal to same, then it will be becoming like 28 by 28 by 1. This will take some time to understand. So, but the point is padding is equal to same if I'm just giving it here. See this, it's got doubled. Why? Because we executed this architecture twice. So again, what we have to start from this particular stage, sequential, and then go back and execute this. All right, fine. Now the original image, if we got it. So what? Just look at its architecture. So originally we had an input image of size 28 by 28 by 1. We upsampled it. Sorry, we just downsampled it by using convo, max pooling, convo, max pooling, convo, max pooling. Right. So till this particular part is an encoding, and again by using convo upsampling we are reconstructing our image 4 by 4. We got it like 8 by 8, and again convo upsampling we got only with respect to upsampling. It is just upsampling by 2 by 2. From 8 by 8 it is getting increased, it is just doubling it up 16 by 16. And again I'm using convo where I'm not giving this particular padding, and then again upsampling 28 by 28. Again I'm using convo layer where exactly I just can decrease this number of features to 1. So now the input image and the output image, input of this architecture and the output of this decoder architecture is the same thing. Able to get my point, everyone? Able to get my point? So I'm just playing with this architecture to just make sure the size is a bit the same. All right. Now we'll just compile it, and then we start training our model. Once we start training, we can just go for a break. All right. So model compilation is done. Compilation is done. Sorry, model construction is done. Let's go for compilation. So what I'll do, model dot compile. So here I'll be picking up my archi, this one. Let me copy this. Let me give it. Maybe let me say I want this Adam architecture or anything. Let's say I'm focused only on this. Loss is fine. Maybe let me pick up this Adam, and loss is nothing but I'm focused on, let's say, so here if I'm looking into this metrics, let me choose this mean square. My loss need to be reduced. Let's say mean square error. How is it? Let's say I want this mean square error because it's not a. Let me use this. Let me try by using this. Now the next step is model after model compilation. It is step number 6 now. Model training. So this is where the most crucial step comes into the picture. Till now, we have not supplied my own image. Now, what I'm going to do, let me supply my image and let me see how exactly this would work. All right. So let me just do this. My input model dot, let me fit my XY batch size. Anyway, it is going to be default batch size itself. If you want, you can give it, but let me not give this. Default batch size will be 32 itself. And let me give validation data. I have it, right? So that's what my X is. And what else we can give it? Maybe epochs. So let me try to take this. Epochs, nothing but one. Epochs, maybe let me start with 5 epochs, maybe. Let me see. Now, what is my input? Input is nothing but my noise images. Where exactly my noise image is available? X train clipped, right? That's where my noise image is. X train clipped. X train clipped. So for this X train clipped, where is the output? That is what should be the exact output that we are giving? X train images. So this X train images is something which is having the original image. An input, we are just going to give a noise image, and the output, we are just going to give this particular clear image. And finally, when we are just applying a noise image with this model's intelligence, when we take it as a .h5 file, whenever we are uploading any image in any website, so we wanted to take, let's say, we wanted to remove this particular noisiness. That's what this application will do. So now behind that scene, there is an intelligence. Now what we do behind that, they have provided this clipped images, that is noise images as input, cleaned images as output, and validation data is nothing but I'm having this X clipped data, right? Say X test clipped data. Last one means we are not worried about it. So let me just train it. Even for 5 epochs itself, it will take some time. All right. So this will take some time. So maybe 5 to 8 minutes. So in the meanwhile, we can take a quick break and we can come back. And then after post break, we will just come back. We will just send one image from the test data. Got it? We will take one image from the test data. We will just feed it to this particular neural network and see the original image of test, because X test clipped data also we have it. The noise images which is available in the test case. So that clipped data we are going to provide it as an input, and we are going to understand how exactly the model is, whether it is clearing this blurriness or not. We are going to check it out. Able to get my point, everyone? Able to understand? Nothing. All right. Fine. Let's go for maybe 7 minutes break. So within that, this will be done. 7 minutes timer. Let me start it. Now the time is 8:12. We will resume at 8:19. Okay. Let's go for a break now. In the meanwhile, this will be done. Okay. I'll be on mute until. Hey, hi everyone. It's all back from break. Jyoti, all right. What about others? Are you all back from break or Anil, Jagdish, Jagdish, Rash? Okay. Perfect. So let's continue this. We are discussing about this autoencoders concept. Where exactly with respect to this architecture, we are trying to provide a noisy data set, and we wanted to remove that noisiness and we wanted to have a clear image. So that architecture we built it. We just built our encoder architecture. We downsampled it. We are taking an input image. We downsampled it and we just represented in one latent space. And that latent space we are expanding it with upsampling point. So finally, we are have built this architecture and we just constructed our network and we trained it. Now let's go back and see. Oh, still, okay, we are at the last epoch. And the last was very high. Okay, we done a mistake here during the training part. See this validation data, I missed it. This is going to be my input, right? Input and output. So how exactly we should have given? So we should have given like X test clip, and here it should be X test, right? We missed it. So anyway, it is not going to get trained for this. Let's anyway evaluate and see. So model training is done. So training 0. Close to 0 anyway. Now let's go and test it. Let's test it, or we can say model evaluation. 7th one, model evaluation, and then we'll go for the prediction. So model dot evaluate we have. And evaluate here we can just provide X and Y. Earlier we missed it, but now let's provide X and Y and let's check it out. So my X is nothing but my, that is input is nothing but my X test clipped, and my Y is nothing but my X test. Now let me see. All right. Fine. The loss is 0.01. That's good. Let's go for the prediction. So for prediction, what I'll do? 8-step model prediction. So for this, first let's try to take all the results. This model is having the intelligence. Model dot, which is having the intelligence, predict, or what we can see usually we'll take it as a H5 file outside. Before that, we'll just check it out, predict. We'll try to pass all this X test noisy images, sorry, clipped images. That's what, because noisy we done, and then we clipped it. So let me provide X test clipped all the 10,000 images. I'm just providing it up, and the final result is getting stored in Y predicted. Y predicted. Now let me see how exactly, in case if I'm just uploading and uploading one image, let's say plt dot im show. Let me see one image. Im show. I wanted to see one image. Next copy. Paste it here. X is equal to. I wanted to take this X test clipped image of 3000, because we are having 500 image for 10,000 images. Let it be gray color. PLT dot show. So the clipped images, all this noise images has been predicted. Sorry, model has been done, and it cleared all this kind of blurriness, and the result, final result is stored in Y predicted. Now what I'll do, let me copy this. Let me change only this particular Y underscore predicted of this 3000. So if I'm seeing this blurriness, it need to go. That's what my expectation. Now see this. I'll just compare it. So we removed all this blurriness. You can check out some other images. 5003. This is this excess clipped image. Now is Y predicted. You're seeing this. Noisiness has been removed off. Now we can take this. Okay, now we are understood. Okay, noisiness is removed. Then finally, what we do, we take it as a deployment. Okay, this model learned well. So what do? I'll just hand over this particular part. The next step is model prediction is done. 9 step. Model deployment. So for deployment, we convert as a .hy file here. So throughout the entire script, where exactly we are having intelligence, this model, because this model is having this same model, not every layer we are just adding it up. So what we'll do, we'll just save this SAV in H5 file. Let's say denoising intelligence, any name, but make sure you're saving it in .hy format. Now this got saved. If you go back, now if you see denoisy.5, 158 KB we have, we take this and we just send it to the team, maybe software development team, or we would be giving it up. And what they do, they just open up a web application. All right, they'll just create one web application, and this is a web application where exactly it is a www dot maybe blur blur blurec.com something. All right, so they will be creating it up, and finally here they'll be creating one new. They'll have upload one. Click here. So once you click it, your image will get uploaded with a lot of blurriness, And once you upload it, so here you'll be having a submit button. They will create like submit button, and then it will get processed. It will be processed, and finally we'll be receiving an output. All right, you will be receiving an output where exactly that blurriness it will be removed, and then here we'll be having a button called download this particular image. So this behind this particular submit button, the intelligence is nothing but .h5 file, what we are giving to the software developers. So the point remains the same. It is a collaborative work to give any intelligence to a web application or a mobile application or to an IoT. If it is an IoT, we collaborate with IoT developers. If it is a web application or mobile application, we collaborate with software developers to accomplish this particular process. And that's the end of Autoencoders. Clear, everyone? Now, any questions? Colored image, yes, we can do that, Srisha. You can just change this one. That is, instead of 1, you can just give it like 3. How we reshaped it. That one small change you can try to give it, and you can just have collect your own data set and take your data set from image data generator, and then try to feed it. The way how we worked on with CNN architecture, the same way you can just try that out. Got my point, what I'm saying? Perfect. All right, I think the first half, we just looked onto the theory. Manthan, Wumpum's world. I'm hearing this part for the first time, Manthan, sorry. Even let me read about it. Wumpum's world. What is that? Completely not aware of this. It says it's a computer game. What is Wumpum's world? It is giving me like a computer game. Manthan, not sure about it. So today we looked on to autoencoders theory part, and there are different types of autoencoders. So you can take a read on like variational autoencoders. Uh, in this way, you can just take a read on and see this types of autoencoders. Read about it. Maybe in future, different types of autoencoders. We are having what we looked on is nothing but denoising autoencoder. We are having sparse autoencoders, deep autoencoders, called contractive autoencoders, undercomplete autoencoders, convolutional autoencoders, or see this noise image encoder, compress suppress decoder. We are getting this. So sparse autoencoder. What exactly this one? And what's that architecture? Contract. The base is this one. All right. But there are different types which you can later go ahead and explore it. Creational autoencoders, applications. Just try to read some blocks later. But the base is nothing but what we learned today. Okay. Any questions? All right, everyone. So that's it for today. So autoencoder theory and also autoencoder script. I hope you understood what we have learned today. Let's meet tomorrow with a new topic. So there are two topics which is left out. One is yes, so detection algorithm, and the other one is text pre-processing. So let's come back. Maybe mostly we'll just get into detection algorithms, and then we'll wind up our image CNN part, that is deep learning part, we'll wind up. And then next Monday, we'll come back. Monday will be our last day, 20th day. We will just get into this natural language processing, how exactly it is done and everything. We will be finding it out. All right. Take care, everyone. See you all tomorrow, same time, 7 o'clock. Good night. Bye, Jyoti. Bye. So, Amar, you can just send this attendance form. Yes, Raj. Good night. Take care, Jagdish.